welcome to this explainer. Today, we're diving straight into the core mathematics of how computers actually simulate the physical world. I mean, have you ever stopped to wonder how engineers just know an airplane wing won't snap in midair long before it's ever actually built? Or how chemists can perfectly predict molecular vibrations without ever looking through a microscope? Well, the secret to all of this lies in a very specific, absolutely beautiful mathematical translation.
We're guided today by a simple yet incredibly profound idea from MIT professor Gilbert Strang. You see, he recognized early on that modeling reality and solving equations, they have to be learned as a unified, exciting process. You really can't just separate the abstract analytical math from the real-world engineering problem. They're deeply intertwined, and honestly, understanding one means you absolutely have to understand the other.
Okay, let's really dive into this. Strang's foundational work essentially acts as our ultimate dictionary for this translation. In computational science and engineering, we can't just feed continuous, winding equations into a computer and expect it to spit out an answer. We have to translate them into a discrete, digital language that a machine can actually digest. So let's unpack exactly how we do that.
This brings us to a huge foundational question. How do we actually teach a computer reality? Think about it. Nature doesn't do pixels or grid lines, right? Heat diffuses perfectly smoothly across a room. A metal spring stretches seamlessly. But a computer? It only understands rigid, discrete steps, ones and zeros. So how do we force this incredibly smooth universe into a jagged digital box without losing the absolute truth of what's happening?
Well, to make reality compute, we rely on what we can call the four great simplifications. It's a bit like stripping a highly complex machine all the way down to its barest bolts. We temporarily pretend that unpredictable nonlinear forces are just simple linear ones. We pretend that continuous space is a discrete grid, that multidimensional objects can be mapped in one dimension first, and that highly variable conditions are just flat constants. Now, obviously, we can't change the reality of nature, but if we can solve the simple, blocky version of reality first, we can start rapidly closing in on the actual truth.
And this is where the magic happens. We completely swap out our mathematical toolkits. Continuous calculus and physical derivatives are suddenly out. Discrete linear algebra and finite differences are in. Instead of zooming in infinitely close to find a perfect derivative curve, like you do in a traditional calculus class, computational math just takes a fixed measurable step and calculates the difference. Suddenly, we aren't wrestling with abstract, winding curves anymore. We're solving massive, rigid grids of numbers.
Which brings us to the real hero of our story, the stiffness matrix. We usually just call it K. This matrix is nature's absolute favorite repeating pattern. It has this incredibly specific sequence on its diagonal, -1, 2, and -1. That pattern, it is actually the discrete digital equivalent of a second derivative in calculus. It's essentially the math comparing a single point in space to its two immediate neighbors. And whether you're looking at a long line of connected springs or a giant steel beam, this exact same matrix shows up over and over again.
Now, what's really fascinating about this matrix is a property mathematicians call being positive definite. In strict matrix math, that just means it has positive pivots and positive eigenvalues. But what does that actually mean for us in the real world? It means stability. It guarantees that if you push down on a suspension bridge, the bridge is going to go down, not spontaneously fly up into the sky. It ensures that our computer simulation doesn't just invent fake energy and explode into total chaos. The mathematical structure perfectly, reliably mirrors physical reality.
So to actually solve these massive grids, computers typically use a technique called Gaussian elimination to break the matrix into triangular pieces, something known as K equals LU. But here's the catch. Standard LU factorization actually ruins the beautiful mirror image symmetry of our original K matrix. And this is where computational math shows its sheer elegance. By factoring out the pivots into a diagonal matrix called D, we get the LDL transpose factorization. It's this brilliant mathematical trick that perfectly preserves nature's exact symmetry right inside the computer's memory.
All right, this brings us to the absolute holy grail of scientific computing, the universal framework. K equals A transpose times C times A. If you take away just one core mathematics concept from this explainer today, let it be this exact framework. It is the invisible underlying architecture behind almost every equilibrium problem across entirely different scientific fields. Think of it as a completely balanced three-part story locked into one elegant equation.
Matrix A draws the geometry. It's the physical blueprint of how different points connect to one another. C is where the real-world materials live. It holds properties like the physical stiffness of a steel spring or the heat conductivity of a copper pipe. And A transpose, that ensures the whole system perfectly balances its internal and external forces. Geometry, materials, and physics all seamlessly balanced together.
So, how do we take this and apply it to a massive, real-world structure? Well, we basically build it like digital Legos. To simulate a massive object, we calculate tiny, local matrices for every single tiny edge or connection in the system. Then we overlap and snap all these tiny building blocks together into one giant, global stiffness matrix.
This snapping together process is the heart of the finite element method. It is the absolute gold standard in modern engineering. Think back to early 3D video games, where round objects were actually made of hundreds of flat, blocky triangles, right? Engineers do the exact same thing to model the smooth aerodynamic curve of an airplane wing. They break it down into simple triangles, calculate the physics for each tiny piece, and then assemble them all back into our A transpose CA framework.
Here is the truly mind-blowing part. This exact same matrix framework doesn't care what science you're studying. It handles the physical stretch of a hanging spring using Hooke's law. It dictates the electrical currents flowing through a circuit board using Ohm's law. It even finds the line of best fit in statistical data analysis using least squares regression. Biology, physics, finance, they all arrive at this exact same positive definite symmetric matrix structure.
But, the universe rarely just stands perfectly still. To step out of a static freeze frame and into the dynamic, moving world, we introduce a mass matrix, M. Now our simple equation evolves into a differential equation. We multiply mass by acceleration, add it to our stiffness, and suddenly our simulation comes alive. We can now accurately model vibrations, the resonance of earthquakes, and traveling sound waves. And this is what allows us to model the extreme extremes of reality. It lets computational chemists track atomic vibrations that happen in just a billionth of a second. It lets automotive engineers crash test virtual cars. That's a problem so violently complex it can require 100,000 tiny time steps and 30 hours of supercomputing just to simulate 1/10 of a second of crumbled metal. Actually, these exact same principles of convection and diffusion even scale over to Wall Street, where they're used to price complex financial derivatives using the Black-Scholes model. Of course, as you can imagine, simulating all of this generates an absolute tsunami of data. To actually make sense of it, like when analyzing tens of thousands of genes simultaneously in biology, scientists rely on another core tool, the singular value decomposition, or SVD. Think of SVD as the ultimate mathematical noise-canceling headphone. It filters out the chaos and extracts only the most critical, fundamental patterns, brilliantly shrinking an impossibly massive computational problem down to just the few variables that actually matter.
These linear models and the A transpose AC framework have given us incredible, truly unprecedented mastery over the physical world. But as we look to the future, facing highly nonlinear mysteries, like the chaotic firing of billions of neurons in the human brain, or the warped space-time of Einstein's relativity, we hit a wall. So the ultimate question remains, how will our computational math have to evolve next to capture the true, untamed complexity of reality?